Okay. So that one's relatively straightforward. That zinc plus copper thing is kind of the textbook example. If you look at pretty much any textbook, you look at Blackman's textbook, there's lovely pictures in there of that reaction happening. When we do the 191 lectures, you'll see those pictures all again. We'll talk about this one. I think it's the first redox reaction we talk about in those lectures. And we start with it because it's a nice straightforward one. But there are a lot of other ones that are a lot more complicated, right? This one has 2 electrons being transferred, but you can have anything up to 7 electrons being transferred in a redox reaction, right? And obviously, and because those electrons will be transferred one at a time, then you can see how these reactions can become horribly complicated, right? Working out how the process is for one electron gets transferred from one to the other, and then the next one, and then the next one. It's all very complicated. And so what that means is that even though in that zinc plus copper 2 plus 1, it's pretty easy to see how you break up the overall equation into half equations and then work out how to do the half equations and work out what's being oxidized and what's being reduced. A lot of the time, that's much more difficult to do. And so one way we can work out which molecules are being oxidized and which are being reduced in some redox reaction that we might come across is to use these things called oxidation numbers. And so it's a series of rules, and oxidation numbers kind of, at the core of them, what you're doing is you're pretending that every compound that you come across is an ionic compound, even when it's not, and you're trying to work out about cations and anions in all compounds, even though, like I say, all compounds are not ionic. So it's kind of a fiddle, or if you want to use the fancy scientific word, it's a formalism. So it's not really real, but that doesn't matter in this case because it still tells us what we want to know, right? So, rules for assigning oxidation numbers. So if you have a chemical equation, and in your chemical equation what you want to do is you want to assign oxidation numbers to all of the atoms in the reactants and all of the atoms in the products, right? So you go through all of the different atoms in the reactants and the products in your chemical reaction, and you work out the oxidation numbers for each of them. And then when you're done with that, what you want to do is you want to go back and look at those oxidation numbers for particular atoms on each side of the equation and see if they change. If none of them change, then it's not redox, right? But if some of them change, then the way that they change gives you a clue as to whether they're being oxidized or reduced. Yeah? So how do we work out the numbers? When atoms exist as elements, they have an oxidation number of 0. So if in your chemical equation you have like sodium, metal, or chlorine, gas, or carbon, or helium, or zinc metal, or anything like that, an element in its standard state, if you like, as just the atom, or for Cl2 it kind of is the same, then those are all assigned as an oxidation number of 0. Right? The oxidation number of a monatomic ion, in other words, an ion which only has one atom in it, so like Na+, Cl-, Mg2+, the oxidation number is the same as the charge on the ion. So if you're copper 2+, copper 2+ has an oxidation number of +2. If you're Cl-, it has an oxidation number of -1. Yeah? Hydrogen almost always has an oxidation number of +1. The only time it's not +1 is when you're talking about compounds called metal hydrides, which we don't do in first year at all anymore. You do them at school, heaven help us. There's a thing called lithium aluminium hydride. Anyone remember that? Sodium borohydride? It's in the organic stuff. It's one of these random reagents that they give you. You can turn a thing into a thing. No one remembers, doesn't matter. Those sorts of compounds are the exceptions, but by and large, all compounds that have hydrogen in, the hydrogen has an oxidation number of +1. Right? Oxygen in just about every compound has an oxidation number of -2. The only time it doesn't is in the compound hydrogen peroxide, where it's -1. Right? But unless you're talking about hydrogen peroxide, the oxygen in any molecule will be 2-. Unless, of course, it's an O2, the element, in which case it's 0. Yeah? And then, in a molecule which has no overall charge, like H2SO4, then the sum of the oxidation numbers of all of the atoms in your molecule equals 0. So for H2SO4, 2 times the oxidation number of the hydrogen plus the oxidation number of the sulfur plus 4 times the oxidation number of the oxygens equals 0. Yeah? Does that make sense? So if the molecule has no overall charge, then the sum of the oxidation numbers must equal 0. And then finally, if you have a molecule which has a charge, so something like ammonium NH4+, then the sum of the oxidation numbers of the atoms in that molecule must equal the charge on the molecule. Right? So those last two rules are kind of the same. If you have a molecule, then the sum of the oxidation numbers has to equal the overall charge. If the overall charge is 0, they have to add up to 0. If the overall charge is something, they have to add up to that something. Yeah? That makes sense? Kind of? So one of these things, I think, once you do a few of them, then it kind of makes more sense. There'll undoubtedly be some to do in the tutorial. Okay, so that's oxidation numbers. So here is nitric acid, HNO3. If we said to you, work out the oxidation number of the nitrogen in HNO3, this is how you would do it. We wouldn't ask you to work out the oxidation number of the hydrogen because you know what that is. It's +1. Yeah? Because this isn't one of those metal hydrides, because we're never going to show you a metal hydride. And you know what the oxidation number of the oxygen is because it's -2. Because this isn't H2O2, it isn't hydrogen peroxide. And so in all molecules, oxygen will be -2. And so what we do is we say that the oxidation number of the nitrogen we can work out because we know that the oxidation number of the hydrogen plus the oxidation number of the nitrogen plus 3 times the oxidation number of the oxygen equals 0. Yeah? Overall, that molecule is neutral, so the sum of the oxidation numbers must equal 0. And then we can say that the oxidation number of the hydrogen is 1, because it's in our rules. And we can say that the oxidation number of the oxygen is -2, because that's in our rules as well. So we can plug those numbers in, and then we can do some math, and we can work out what the value for the nitrogen is. And I've done some rearranging there. If you're up for rearranging these ones, then that's fine. But oftentimes, I think you can just look at them and work it out. I think it kind of makes sense. It's always probably one of those calculations that's a good idea once you come up with an answer, so you work out that it's +5, or you think it's +5, to put the +5 back into here, and then do the math again and make sure it still adds up to 0. Because it's quite easy sometimes, instead of getting +5, to get -5. If you just do that little bit of rearranging wrong, so it's always a good idea to go back and check. Yeah? And so here the oxidation number for the nitrogen would be +5. Now what you find is that for things like nitrogen and sulfur and phosphorus and a lot of atoms, they can have lots of different oxidation numbers. Even things like chlorine and bromine and iodine, you'd think they're always going to be -1, but they're not. Depending on the molecule, they can have lots of different oxidation numbers. The only ones that don't really change at all are hydrogen and oxygen. Okay? Right, so how can oxidation numbers help us work out if this reaction is an oxidation or a reduction? So here's one of the old favourites, purple permanganate. Anyone not done anything with permanganate before? One person. I'm sure we do this in a lab at some point. So this is that dark purple stuff that goes colourless when you do reactions with it. So permanganate has the formula MnO4-. It's a manganese with 4 oxygens attached to it. And if you mix it up with some acid, then you can write an equation like this, where the permanganate turns into manganese 2+, and the H+ gets incorporated into water molecules. So that equation as it stands is balanced. And the question is this a redox reaction or not? And so what we're going to do is we're going to go through and work out the oxidation number of each element before and after the reaction. So work out the oxidation number of the manganese in the reactant, and the manganese in the product, and the oxygen in the reactant and the product, and the hydrogen in the reactant and the product. And we're going to see if any of the oxidation numbers change when the reaction happens. If none of them change, it's not a redox reaction. So if you were to do this for or any of the reactions that we did yesterday, you should see no change in the oxidation numbers, because those were all acid-base reactions. They weren't redox. Yeah? But if we look at it, we can see that that the H's are all incorporated. There's no H2 gases, right? It's H+, and it's H2O, and it's O in a molecule, and then it's O in a molecule. So what that means is that the H's and the O's aren't going to change their oxidation numbers. Right? They're only going to change if you made hydrogen peroxide, say, out of the oxygen, or if the oxygen went from O in a molecule to O2, yeah? To its elemental form, if you like. Or the H somehow changed into H2, its elemental form. None of that happens here. I mean, you can go through and work it out if you want, but none of that happens here. So that means that the oxygens and the hydrogens won't change their oxidation numbers in this reaction. There's going to be +1 for the hydrogen in the reactant and the product. It's going to be -2 for the oxygen in the reactant and the product. So we only have to worry about the manganese, yeah, the Mn. And so we can work out the oxidation number of the manganese in the permanganate ion like this. Is going to be the oxidation number of the manganese plus 4 times the oxidation number of the oxygen, and all of that needs to add up to -1, the charge on the ion overall. And so we can put in our numbers. Well, in fact, that's done some rearranging as well. Heaven help us. So the oxidation number of the manganese is equal to -1, the overall charge, minus 4 times -2, where -2 is the oxidation number of the oxygen. And you can work out that the manganese's oxidation... see, should have more coffee. The manganese's oxidation number is +7. So in the reactant, the oxidation number for the manganese is +7. In the product, what is the oxidation number of the manganese going to be? +2, yeah? Because the product is just manganese 2+. And remember, the rule says that if it's a monatomic ion, then the oxidation number is the same as the charge. Right? So in the product, it's just going to be +2. And so what we can say then is that during the reaction, the oxidation number of the manganese has decreased from +7 to +2. And if the oxidation number decreases, then that's going to be a reduction. So if you like, the oxidation number has reduced from +7 to +2. It's got smaller. And so not only does this tell you that this is in fact a redox equation, it tells you that it's in fact a redox half equation, and it tells you that it's a reduction. Yeah? Even though there's no electrons in there, just by using the oxidation numbers, we can work out that it must be a reduction. So in general, we can say that by considering the way that the oxidation numbers change on going from the atom being in the reactants to the products, a reduction is where you have a decrease in the oxidation number, and so an oxidation is where you have an increase in the oxidation number. And so because the oxidation number of the manganese decreases from +7 to +2 in this reaction, we can say that the permanganate is reduced to manganese 2+ in this reaction. And if it's reduced, does that mean it's gained electrons or lost electrons? Gained electrons, right? That equation as it stands doesn't have any electrons in it yet, but we don't need them there to know that it's a reduction because we can use the oxidation numbers. Yeah? So if you like, I mean, like I say, normally what we will do is we'll give you an overall reaction and we'll say pull this apart, write out the half equations, then put it back together again. But sometimes you don't want to do all that. Sometimes you just want to look at it and go, is this an oxidation or a reduction? And so the oxidation numbers give you a way to sort of quickly do that. This is something if you go on to do biochemistry, biochemistry is littered with redox reactions, and yet you'll hardly ever see any electrons written in the equations because they don't care, right? But you need to be able to recognize whether a particular reaction is a reduction or an oxidation, and so oxidation numbers can give you a nice quick way of working that out.